So let's continue that conversation. So basically, if the radium is losing 2 protons and it had 88, I mean, let's do some simple math here, right? 88 minus 2 is 86. So the new element that's left over is going to be the element with 86 protons. The mass having 226 to start, losing 4, it's now going to be 222. So just by doing math, and I'm going to write this all out for you when we actually start to practice this, but those are the top and bottom numbers. Those are the mass numbers and the atomic numbers that you should be left with. And then just using our resources and using the skills that we already know, go to the reference table, find out that atomic number 86 actually belongs to Rn, and we've completed our first nuclear equation for an alpha decay. So this is a radioactive equation where and a transmutation, where one element turns into another by losing some sort of particle in the process. Okay, so that's alpha decay, and that's how this reaction works out. So I'm going to kind of go through the rest of them. Alpha, beta, positron. I can't remember if we do positron or not, but we're going to go through them, whatever we have in here. And then we're going to practice it in the next lesson. So, we did that one. So our types of decay continued would be beta particle coming in next. Now, make sure you have your reference table still out because we're going to do it. A beta particle is a high-speed electron or a positron. Could be one or the other, and you're going to see there are two different types of beta decays. But generally speaking, beta could be giving off an electron or a positron. And we'll go to table O to write down the two notations for each. So if I write this here, let's see if I can do this, right? The positron notation, which is right here, there we go, right here, is a 0 mass and a +1 atomic number with either an E or a B. That is called a positron particle. Now, the reference table doesn't really exactly do justice to the difference between beta decay that's a positive beta decay and beta decay that's a negative beta decay. It kind of just lumps negative beta decay as a beta particle. I'll talk about this a little bit more in the next few slides. But a beta particle, come on, bud. Come on. There we go. A beta particle is a 0 mass number with a minus atomic number. And it can be written in one or the two ways. So, according to the reference table, a beta particle is the -0, and a positron, well, actually, they're both beta particles. The difference is positive beta and negative beta. The reference table doesn't really go into that, but I think you can tell the difference between which one's a positive beta, and which one's a positive beta, and which one's a negative beta. Yeah, I think we'll talk more about that as we go. But generally speaking, those two types of beta particles are either positive or negative. I hope I didn't confuse you right there, but I think I'm going to clarify it right here. So, cover that up so you can make you think a little. So a negative beta decay is the negative version of what we were talking about. That's that electron. That's the -1 beta particle. Or this one. Okay? Those are the two symbols for a negative beta decay. And basically what happens is a neutron breaks down into a proton and an electron. So, I mean, if you can think about it, right? We have a neutron. Normally we say that a neutron is neutral. It has no charge. But the reality of it is a neutron actually has both the positive and the negative parts in it. And that's what actually makes it neutral. It's not that it doesn't have a charge, it's that inside of it, there's a positive and a negative. And so at some point, if the nucleus becomes super unstable, one of the neutrons might break apart. And when it breaks apart, it actually separates into the positive and the negative. And this stays and this leaves. So an electron is shot out and a proton stays behind. So I think I have a nice picture of it here, right? So the neutron that you start with becomes both a negative electron and leaves behind a positive proton. And this is called a negative beta decay. Now, don't get bogged down by the fact of the negative. Just make the connection between the negative beta and the negative symbol in the equation. So let's look at another equation that we'll explore more as we go. But thorium is the atomic number of 90. It's unstable. It undergoes negative beta decays. If it were to do such a thing, right? Well, I guess we're going to see it, right? If it were to do such a thing, the atomic number would actually increase. So not every time transmutation takes place do we see the element drop in atomic numbers. Sometimes it can actually go from, like you're seeing right here, from 90 to 91. And I hope, based off of what I was just kind of explaining here, that makes sense, right? The neutron wasn't a proton. It was a neutron. It broke apart into something that was negative and into something that was positive. And if it leaves behind a proton, the atomic number goes up. We've added a proton. Maybe adding is not a good word to use, right? Because we didn't necessarily add it. We changed a neutron into a proton. And so the atomic number has to go up. So here's something we're going to practice a lot, right? Is using our math skills to apply this. Now, knowing that the beta decay is written like this, okay, we can do math. That might be scary for some of you. But remember, the one thing is always true. Whatever we start with, we have to end with. Conservation of mass, conservation of energy, conservation of a lot of different sorts of things. But if I had 90 protons, we're going to refer to it as 90 bottom numbers. We got to have 90 on the other side. And so if you just add everything up and you do 90 plus minus 1, 90 equals 91 plus minus 1. And the same has to be true up top, right? The mass didn't change in this decay. It stayed the same. Why? Because neutrons and protons have the same mass. Electrons don't have mass. So if a neutron changes into a proton, both having the same mass, there's no change in the total mass of this element, of this atom. All right? So let's look at a positive beta decay. In this case, a proton releases something called a positron, and then it becomes a neutron. Now that part, like what is actually happening, knowing this, you don't need to know, but it helps to understand what's going on over here. So remember how I was just saying neutrons are partially positive and partially negative, and protons are entirely positive and electrons are entirely negative. Well, what can happen in some nuclear decays is the thing that makes the proton positive leaves. The little positive guy. That's called a positron. Now you can't see it here because it looks like a negative, so I shouldn't really have done that. Right? That is the symbol for a positron. There we go. This is the same thing. Okay, a positron has been emitted. I should probably move that out of the way. And when a proton loses what makes it positive, it now has no charge. So it reverts back into a neutron, so to speak. That's called a positive beta decay. Proton becomes a neutron because it loses what makes it positive. Now, if we look at that in the equation, we kind of apply the same stuff that we were talking about, but I'm going to use the picture and the equation to kind of show you. I started out with carbon 6. It had 6 protons. If it undergoes positive beta decay, it's going to give off this particle right here. Okay, these two things, I'm going to show you where you can get that information. It's nothing that you're going to have to memorize. But if this is going to give off this, we're going to have to figure out what this is. Now, if you know it, if you know that a proton gives off the little positive part and then becomes a neutron, you would kind of be able to just quickly say, oh, well, if a proton becomes a neutron, there's one less proton. And if there's one less proton, the atomic number's got to go down. And that's what we're seeing. The 6 protons have now become 5 protons because one of those 6 turned into a neutron. Okay, so again, we can look at it like this. Okay, just doing math. Right, do all the bottom numbers on the left side and the right side of the equation match up? Of course they do, right? 6 is equal to 5 plus 1. And we know that we've balanced this out. All right, do all the top numbers make sense? 11 equals 11 plus 0? Yeah, that makes sense too. And that should make even more sense intuitively because protons have a mass of 1. Neutrons have a mass of 1. If I turned this proton into a neutron, the mass wouldn't change. It's almost like saying if I took an apple and every atom in that apple turned into an orange, what would happen to the mass? It would stay the same, right? Because they're the same amount of atoms in each fruit. All right, I got one more for you. All right, and then a little picture, and then we're out of here for the day. So, gamma rays. Where are we here? Well, too late. Gamma rays. High energy. Gamma rays. No mass. No charge. Just energy. They have the greatest penetrating power. These types of things are X-rays and photons. Okay, the symbol, which is also on table O, is right there. It's a little gamma letter, Greek letter gamma. So, I'm going to ask this question to any of you comic nerds. Kind of gave you a little bit of a hint there. Where are gamma rays significant? What superhero is known for using or being used by gamma rays? The Hulk. Bruce Banner. And what was the Hulk's greatest superpower? His super strength. And gamma rays, which created the Hulk, have the greatest penetrating power. Just like the Hulk can smash through anything. But what I really mean about the greatest penetrating power is gamma rays can go through concrete. Gamma rays can go through walls. Gamma rays go through bodies. Right? Gamma rays are the most dangerous out of the 3 that we're talking about. And this really kind of coincides with how many different surfaces or how many different can't think of the word right now, but surfaces that it can go through, and that makes it dangerous. Now, the fact that it also is high energy, that's where you start talking about mutations in your cells, in your DNA, in your body, and that makes it more detrimental, right? It makes it the scariest. Okay, so the good news is gamma rays leave the nucleus, does not change the element.